All right, welcome back. I hope that you are all hydrated and ready to enjoy a little bit of quantum computing. This ought to melt your brain a little bit. I'm very excited about this, especially to see how the cloud is making this a lot more accessible than trying to have your own lab with a quantum computer in it now. So without further ado, I will toss it over to Sassy, who's going to teach us all about quantum mechanics. Have at it, Sassy. Cheers.
Thanks, Nate. Okay, let's explore some quantum computing today in this session. But before we jump into quantum computing, little bit about me. I'm Ceci Perry. I work for Cardinal Health, which is a largest drugs and medical supplies company ranked 14th by Fortune 500. And I also occasionally contribute to open source projects. And here is my disclaimer. So today in this session, I'll first talk about a little bit of quantum physics, basically quantum particles and their behavior, very high level, just enough and is relevant to be able to understand quantum computing. Then we will see what is quantum computing, why is it relevant today, and its significance. And then we see how we can get involved today. And we will see that with the help of Java QC API called Strange. And then we will conclude by looking into a few use cases and key takeaways. And there will be a separate Zoom session for Q&A. Now, the first thing is superposition. Let's try to understand what superposition is by looking at a couple of scientific findings and experiments. The first one is double slit experiment. So what scientists did was that they shot a photon into a black box that has two slits. And what they expected to see was that the photon travels through one slit and make a dot. But to their surprise, what it did was it created this interference pattern, as if the photon was traveling through both slits at the same time. And perplexed by this, they thought they will watch this closely and see how this is traveling through both slits at the same time. When they started watching, observing, it behaved like a particle, not like a wave anymore. It went through only one slit and made a dot. When they observed and when they did not observe, it behaved differently. The other example that I picked is from nuclear physics. Apparently, lead 186 can be in three different shapes superimposed all at the same time until observed. When you observe, it picks a shape and collapses to that shape. So putting this all together in a nutshell and summarize, subatomic particles in nature can be in multiple states all at the same time. Multiple possibilities can collapse into one single probability with slightest interference. And the non-deterministic nature can turn into deterministic only when observed, only when you look at it. And the other thing is entanglement. Quantum particles, again in nature, could be intertwined. They stay connected, and action on one can impact the other one instantaneously, independent of the distance, like shown here. And you cannot determine state of one independent of the other. Scientists proved this at space scale. What they did was that they shot a pair of entangled electrons up and they sent one to China, the other one to Austria. And when they decided to observe the first particle in the lab one and measure the spin to be up or down, instantaneously at the same time, the other particle in the other lab chose to lose its superposition and collapse to a state up or down. That's entanglement in a nutshell. Now coming to quantum computing and quantum computers and how what we just discussed is relevant to quantum computers. There are many remarkable inventions mimicking the nature or inspired by the nature. For example, Velcro was invented mimicking the burdock plant. And apparently, Wright brothers were watching the birds for so long before they were inspired to make an airplane. Similarly, quantum computers mimic the laws of quantum physics. Electrons kept in superpositions, quantum states such as superpositions are the building blocks. That's why it is often said to be very close to how nature works. And because the quantum computers are created, the hardware essentially, by keeping the electrons in superposition, it can create the possibilities that normal classical computers may not be able to create. And particularly, the quantum computers are good at the problems that involve space and time complexities. We will see more about this space and time complexity later. But before that, the fundamental unit. We all know in the classical systems, the fundamental unit is a bit, which could be 0 or 1. However, the fundamental unit in quantum computer is qubit. And because the qubit is created by keeping electrons in superposition, it can be in multiple states at the same time. The qubit can be 0 and 1 at the same time. More accurately speaking, it is a linear combination of 0 and 1, more like how this formula represents, where alpha and beta are the probabilities for this qubit to be able to collapse into 0 or 1. Basically, alpha and beta represent the amplitudes. And I found a great analogy by Chuck Bates, who is a physicist. He says if bit is like a switch that can be on or off, the qubit in superposition is more like a dimmer. Now let's see the time and space complexity thing. To explain that, I made this table. The leftmost column shows the number of qubits, like 1, 2, 3, 4. And the right column shows the number of equivalent bits if you have to represent the qubits in the classical way using the bits. And how I arrived at this calculation is what this middle columns explain. Given a qubit, it can be in two states, 0, 1. That's 2 power 1. And 2 would be 4 states or 4 paths, that's 2 power 2. And that means the number of bits would be 2, 2 into 4, 8, and so on. So as you can see, it's going 2 exponents. And if you extrapolate that further, 64 qubits would be 2 power 64 simultaneous paths for the quantum computer, and 1 million terabytes. But if you have to use a classical bit to process these many paths, traverse through them one after another sequentially, it would take apparently 400 years minimum. And similarly, if you extrapolate further, through 300 qubits would be equivalent to the number of states that's greater than all the molecules that we can count in the universe. And it would be 90 zeros after 2 if you represent that in the bits. And I can't even imagine how many thousands of years that would be for a classical computer to traverse through all these paths. Now, how do you make a qubit? Google and IBM use superconductors to make their qubits, which means the hardware needs to be kept at absolute zero temperature. That means colder than space. Whenever I imagine the electrons, why do you have to keep colder? Because that's when the superconductivity will be at its max. So when I imagine these electrons freely flowing with no resistance, always somehow the Dash of Incredible movie comes to my mind, because he moves so fast that my eyes cannot even follow. He appears as if he is in multiple positions at the same time. Now think about it. How else can you make an electron, put an electron in multiple positions at the same time? Maybe by splitting it and put those pieces into multiple positions. That's the basic idea behind the topological qubit. And Microsoft uses that technique to make topological type of qubit. And there are other ways of making it that are being researched and explored, but most of the other ideas are still at academic level. Now, how can we get involved? So we saw slightest interference can collapse the system, and we saw that the fault-tolerant hardware is not yet available, and it's not abstracted at all levels. So if these many not available things are there, then why am I even talking about quantum computing? Can we even do anything about it, get involved? The good news is that the companies like IBM are exposing the real quantum computers, the real hardware that's running in their labs via cloud, and they have a UI. As a matter of fact, right now you can go register and start exploring. I have the links in the reference section that you can try out. And not only that, we have a whole lot of hardware simulators written in multiple languages. Coming to software, there are lots of SDKs and APIs available in multiple languages like Q Sharp, Microsoft, QCWare's Python, OpenQuasm, IBM. But guess what? When I was looking for such software, SDKs, or APIs, somehow all possibilities collapsed into one single thing called Java. And thus, I landed on this. It's strange, a Java QC API started by Johan Vos. And it's an open source project licensed under BSD. So the Strange API itself has multiple layers in it. The lower level or the core API is more closer to the quantum gates. Um, like you will program using the Hadamard gate or quantum gates, but the higher level API abstract these details and it looks more like your regular classical programming. And then it also has an execution environment, which is a simulator environment. And besides, there is another library called Strange Java FX library, which will be used to render these circuits and visually represent them, which will be useful to debug and visualize the circuits. And we will at this point go into demo and then see a little bit of the code. But before that, one more thing is, how do you go about writing the software? The first key thing is to identify the right problem. When I say right problem, we will see what I mean by that in the later slides. But then after you identify the right problem, you transform that to suit into the QC algorithm. What I mean by that is explained very well in this link that I included step by step. Due to time constraints, I cannot go into the detail, but it is around an idea of a function hidden in a black box called Oracle. And the job is to identify what is hidden. After identifying the problem and transforming, you go about writing the algorithm. And Strange itself implemented a few of such algorithms like Deutsche, which is a deterministic algorithm. And based on the output, the algorithms could be deterministic or probabilistic, like Grovers and Shores are probabilistic. Let's at this point go into some code. So I'm going to talk about this Strange and show. First, I'll go about the lower level API. Then we will move on to the higher level API. And the first thing, though, is to see what do you need to run these Strange based programs. So the core dependency is Strange itself. And I commented that, but I have Strange effects, which is the UI aspect that I was talking about. That's because this transitively gets the Strange. And now the first thing I'm going to show you, as far as the lower level API, is the Hadamard gate. Hadamard gate in quantum world is used to create a superposition situation. And the first line here you see is the execution environment. It's a simulated execution environment. Then I'm asking for 1 qubit, and then I keep adding steps. The steps could be some logic or gates. Here in this case, I add a Hadamard gate, and then at the end, I measure this qubit and see what it is going to collapse it to. And then this last line renders the circuit. And then the second method is exactly the same code, but I would run it 1,000 times in an iteration. We will see why I do that. And let's run this program and then see what happens. And it's supposed to bring me up the circuit. So I got 1 qubit, sent it through Hadamard gate, and at the end I measured. And when in the first execution, it's collapsed to 0. So it was in superposition. When measured, it collapsed to 0. But I can, by running single execution, I cannot prove that it once was in superposition and between 0 and 1. So that's why I had to run 1,000 times. And when measured, you can see 471 times it was measured 0, and rest of the times 1. Almost 50-50. That shows that it once was in superposition. And the other example I would show is how you make an entanglement. So this code looks similarly like the last one. The only difference is that here I ask for 2 qubits. The first one goes through Hadamard gate, the other one via C0, and then it renders. Now let's run this and see. And what happens. And it's supposed to again bring me some circuit. So here, the first one was sent to Hadamard gate, and the second one via C0 gate. So the C0 gate is slightly different from the classical NOT gate in that C0 gate flips the second bit only when the first bit is measured 0. That means if the first one is going through Hadamard gate and is measured 0, the second bit does nothing. That means it is still 0. But if this is measured 1, then it flips via x-axis and it becomes 1. So this probability graph shows like what happened actually. So here you can see when it is run 1,000 times, 0, 0, 1, 1. That means every time the first one is 0, the second one is also measured 0. And when it was measured 1, this one is also 1. That shows that they are entangled, related to each other. Now let's see the higher level aspect of it. That I would show using something called Grover's algorithm. So the Strange implemented few algorithms as I was talking. Now this classic.search is calling that higher level API. Grover's algorithm is a search-based algorithm used on larger sample sets where you want to try finding the items. Here I have a list of animals and I'm trying to find where cow is, whether it is there in the list and where is it. And first we will run this and then I will explain more. And if I run right here, and then it said the winner is 2, that means index 2, 0, 1, 2, which is correct. And it predicted that with 94 confidence. So if you run more times, the confidence will increase. And it's a 2.2 steps. Now, the 2.2 steps, I will not go very much into the detail, but at a very high level, what it is saying is that what Grover's algorithm guarantees is that it is guaranteed to find the value you are looking for in less than square root n. N is the total number of items in the set sample size. And why is that? I'll give very high level where that square root n is coming from. In a classical system, if you are traversing through these elements one by one, the best possibility is that you find the element at the first place. The worst possibility is at the tail end, right? If you are going one by one. However, if you are using quantum computer to produce all the possibilities at the same time, how many qubits would you need? We saw the two complements where the complement is the qubit and the possibilities would be 2 power whatever is the complement. So if you want to calculate how many qubits this would be, for example, like if n is the total number, and if you are representing that with 2 power some x, the x is what the qubits. So that's where that means x is equal to square root of n. That's where that square root n concept is coming. But it is not as simple as that. There is something called reversibility and all that. But you get an idea of where that square root n is coming from. And now let's go back to the presentation again. So if you write the algorithm, I just included a picture. A circuit probably would look something like this at the end with some interference, some amplitudes going up or some are nullifying. And then use cases. These are a couple of areas that are being researched, but my most favorite use case is healthcare. There is personalized drug manufacturing. The reason is this. The drug manufacturing itself is chemical reactions, and then where they are administered on the human body, it interacts differently with each human body. And so the chemical reaction itself is inherently quantum. And when it is interacting with the body, again, it's a quantum. So what would be a best system to simulate a quantum system? It would be quantum system, not the classical system. That's why I like this example. Imagine that the quantum computers are used to test the vaccine, how fast the result could be. And the second best example that I like is QKD, which is the idea behind keeping the quantum particles in entanglement and exchange the information, which is more like the space experiment that I shared in the second or third slide. And there are other areas like quantum cryptography, banking, AI/ML. And in the interim, there is some fun stuff also that we could do, which is like games. People are creating games. And then another thing that I liked is James Weaver's presentation. I think in 2016 or something, it's a lightning talk where he creates the quantum music using quantum circuits. I liked it very much. If you have a couple of minutes, you may want to watch that. That's a hyperlink. And then coming to takeaways, use QC only for the right problem. So what is the right problem? Like I said, if you are working with a problem that's inherently quantum, then you want to use quantum system to simulate it, test it. The second thing is like an optimization problem where there is this time and space complexities are involved. Otherwise, it's a overkill. It's too costly. And like we already discussed, the fault-tolerant hardware that's abstracted at all levels is still a challenge. It doesn't exist. So what that means is that your bank accounts are not going to be broken anytime soon, because this is the idea that Shor's algorithm, which is a prime factor based, is going to break all the bank accounts, right? But the fact is that Shor's algorithm expects a big fault tolerant computer, quantum computer, which is far from reality. Plus, there are already research going on to remediate these things, like black DAG instead of chain, I think, some tangling aspects. The third point is that you can get your hands dirty, like we saw with Strange. And the other important thing, very important thing, the fourth point is that the quantum simulators are simulators using classical computer, and we are simulating the quantum world. That means they're very memory hungry. That means they're meant to test only logic on small scale, and to prove that the logic works. And what I spoke today is a very high level, like, scratching the surface. And there are other areas to be, discussed, such as quantum networks and teleportation. If you want to deep dive, I have a link section where I included very rich information and a whole lot of links, and also the Git repository that has the sample code by Johan Vos and others. And because now we have time, I actually have a game running on my computer. I think I have time to show that. But before that, I would like to thank a few people here. The first and foremost is Jim Shingler, and then Ralph Meira, who for his valuable feedback and being a good critic, and my cardinal friends, Tom Halter and Doug Hook. And these are the links I was talking about. This is the Git repository. And this link here, the David Deutsche himself, it's a video talking and going in depth with these algorithms, and especially the Grover's algorithm. He explains it very well. And here are the links where you can register and then experiment. Now that we have like 4 minutes, I would show some fun game to understand these quantum gates. So this is called Mary Has a Qubit. It's again created by Johan Vos, not me. And originally this kind of a game was created by, I think, Stephen, a technical lead in OpenJDK project, to explain lambdas. And Johan got inspired by this, and he made a similar thing to explain the quantum gates. Let's see. I'm just showing to show the fun behind, and then the game's possibility. So here, this is Mary. When he visits the barn, she gets a qubit, and this is a Hadamard gate when she visits, and this is CNOT gate and poly gate and so on. So now let's see how this works. So she visited the barn, she got a qubit, and then she visited the nest, and Hadamard gate is activated. When the lamb visits that gate again, see here the circuit is rendered. Now let's send Mary through the barn again. She got another qubit, and now let's do some entanglement, the CNOT gate activation. Now she visited that, the CNOT gate has been activated. Now lambs visiting that gate are going to go through CNOT, see the CNOT is created. Now the church here, when they go through that, it collapses to, the observing effect happens, and it collapses to a state, and it measured at 0. Finally, thank you all. Let's go back to presentation and see if I have anything else. No, I don't. So thank you all for attending this presentation, and I will see you back on the Zoom session with questions and answers. And there is a Slack channel also if you want to go further in any of these things that we discussed. And I hope that you are excited enough about this quantum computing. That's the whole idea about putting this presentation together for 25 minutes.
Awesome. Well, thank you so much for jamming an awful lot of information into a short amount of time. We really appreciate that. Please do follow us over into the Q&A if you have some questions, if you want to keep that discussion going. So thank you so much, Sassy. That was amazing. It reminds me of that Gibson quote, the future's already here. It's just not evenly distributed. So thank you very much for doing your best to help us understand this quantum computing future a bit better. With that, we're going to take a short break, get up, maybe do some light stretches, maybe a little bit of yoga, get ready. We're kind of in that final stretch here, just a couple more hours to go. So let's power through. Thanks, everybody.